Yeah. Welcome to this evening's chemistry class. Last week we started talking about the kinetic theory of gases. Where we talked about the phenomenon supporting the gas theory and other things that are involved. So today we'll be talking about the gas laws. I gave an assignment and only few people were able to submit it. It's nice and it was quite a good trial. So let me just do a recap. So based on assignment, one of the assignments was why are electrovalent compounds stronger than covalent compounds? It's simple. The reason is electrovalent compounds are formed due to transfer of electrons, while covalent compounds are formed due to pairing and sharing of electrons. So when there's a transfer of electron, the bonds are stronger. Hence, those type of compounds do not break easily compared to those of covalent compounds. So that's it. So today we'll be moving directly to gas laws. So some of the things we're taking is behavior of an ideal gas, Boyle's law, Charles' law, the general gas equation, Dalton's law of partial pressure, ideal gas equation, Gay-Lussac's law, and Avogadro's law. So let's move first of all to the behavior of ideal gas. Now, the behavior of ideal gas is guided by the kinetic theory of gases. If you remember, last week we said the kinetic theory of gases says that, or kinetic theory says that all particles of all matter are made up of tiny particles that are in constant motion. So now, the kinetic theory of gases explains the behavior of ideal gases as follows. One being that gas molecules move in random straight lines, and when they move in these random straight lines, they collide with each other and with the walls of their container. So their movement is zigzag-like, just like we said, like Brownian motion, zigzag-like, not directional, but in straight lines. And then the second one states that the collision of the molecules are perfectly elastic. Now, when we say they are perfectly elastic, it means when they bombard or when they hit each other, what happens is they have an amount of energy as they are coming to hit each other. Now, they do not change this energy. What happens is the energy remains constant. There might be a transfer of the energy or an increase, just like your snooker ball. I know many of us have seen where they play snooker. The first ball that is hit by the stick carries an amount of force and hits other balls. Now, it's not that the energy is lost by that ball, but it is transferred. So that is the elasticity we are talking about there. So when the gas particles hit each other, they transfer this energy. It's not energy is lost. Now, occupied by, you can actually notice, but for gases, it is negligible. It's something you can do away with. And just like last week, we said the gases move freely. So the coercive forces between the molecules of the gases actually is also negligible. Now, what about the temperature? Temperature of gas is a product of their kinetic energy. Remember, these gases are coming with force to hit each other. With this force they are coming with, it causes a release of energy. And this is dissipated and is felt around them. So these are the behaviors of an ideal gas, a perfect gas. So now, with these, we'll now talk about the laws that gases obey. We'll start with, okay, before we move to that, please, let's still talk about some things like gas pressure. Um, Gas pressure is the force that's exerted per unit area of the wall of the container. The amount of force exerted by the gas per area of the container in which it is found in is gas pressure. And it is measured in atmosphere or millimeter mercury. That mmHg we are seeing there is millimeter mercury. And this SI unit, or the international standard unit for pressure, is Pascal or Newton per meter square. Now, the relationship between ATM, Newton per meter square, and millimeter mercury is for one ATM, we have 101,325 Newton per meter square, which is still equal to 760 millimeter mercury. We can still put this as this. It's the same thing as saying 7 days equals to 1 week, right? And a dozen is the same thing as 12. So one ATM is the same value as 101,325 Newton per meter square, or the same value 760 millimeter mercury. Please take note of this. It's very, very important. Why this is important is because of what we call STP, which is the standard at 0 degrees or 273 Kelvin. 0 degrees or 273 Kelvin. While for the pressure is 760 millimeter mercury or 1.01 times 10 raised Newton per meter square. Sorry about that, it should be 5, not minus 5. 5, not minus 5, please. Now, what is the implication of this? Meaning that for a gas at a particular standard temperature, when you say gas at standard temperature and pressure, it means that gas will either be at 0 degrees Celsius or it will be at 273 Kelvin for the temperature. While for the pressure, it will be at 760 millimeter mercury or supposed to look like. So V is your y-axis and 1/p is your x-axis. So because they are inverse to each other, it forms a straight line from V to P. Now, what is the implication of this? Let's take this example here. 375 centimeter cube of a gas has a pressure of 770 millimeter mercury. Then we are trying to find the volume. If its pressure is reduced to 750 millimeter mercury. Now, we're using the formula P1V1 equals P2V2. We have our P1 there as 770 millimeter mercury. That is our first pressure at 770 millimeter mercury. Then our V1, look at it there. We are told that 375 centimeter cube of a gas. That is the volume that the gas occupies. Now, we are told that we should now look for the volume, that is your V2, if your pressure, your P2 is reduced to 750 millimeter mercury. So when you are trying to solve questions like this, to be good, you try to understand, okay, from the units that I am given, what am I looking for? Or what parameters am I given? So let's remember the formula. When you have, okay, your pressure and volume, when you have only pressure and volume given, know that the formula to use is your Boyle's law, which is P1V1 equals P2V2. So we solved it there as, since you are looking for V2, we have V2 equals to 770 times 375. 375 is your V1, right? So that is your P1 times your V1 divided by your P2, which is 750. If you try that, you will get 385. Please, can we try and calculate on our own? just try and get this out. P1 V1 equals P2 V2. Then put your parameters, use your calculator. When you try it, you will get 385 centimeter cube. Please, this question, sometimes questions like this come out in external examination. Please, let's take note of it. Now, that is for Boyle's law. Now, we'll move to the next law. Or is there any question so far on that? Do you have any question? Okay, so if it's understood, let's move on to the next one, Charles' law. Charles' law. So Charles' law states that the volume of a given mass of, sorry? Okay. So Charles' law states that the volume of a given mass of gas is directly proportional to the temperature in Kelvin. Specifically, the volume of a given mass of gas is directly proportional to its temperature in Kelvin, provided the pressure remains constant. So this time around, pressure is constant. Pressure is the constant there. Now, this, so what that means is V, as we see there in the next line,
Emmanuel, please mute yourself. Emmanuel and Lizzie, please, both of you should mute yourself.
So V is directly proportional to T. So when we now introduce the proportionality sign or the equality sign or the constant, we now have V equals to KT. So if we make K the subject of the formula, that is a constant instead of the formula, we have V over T. Remember, K is the constant there. Now, mathematically speaking, that will be V1 T1. Sorry, V1 T1 equals to V2 T2. Sorry about the mistake there. It should be V1 T1 equals to V2. Oh, sorry, V1 T1 over V2 T2. Since we have it as V over T, so V1 T1 equals to V2 T. Sorry, yeah, V2 T2. Yes. So, now remember that what we said there is that it should always be in Kelvin. And taking it back from what we have on this slide, that our gas temperature is usually 0 or 273. So that means you must convert whatever value you have to Kelvin. You must convert whatever value you have to Kelvin. And converting it to Kelvin is 0 degrees C is equal to 273 Kelvin. That is, for every 0 degrees is equal to 273 Kelvin. Or minus 273 degrees C is equal to 0 Kelvin. What's the implication of that? That means if you are given a temperature in Kelvin, for you to find it in degrees Celsius, or if you are given a particular value, and okay, let's say now you have 10 degrees Celsius. For you to find it in Kelvin, all you have to do is you add 273. So that will be 10 plus 273. It will give you 283. That would be the value of that temperature in Kelvin. But let us say you are given in Kelvin and you're trying to now change it back to degrees Celsius. All you have to do is that Kelvin temperature minus 273. For example, let's say you are given the temperature in Kelvin as 283 degrees Kelvin or 283 Kelvin. And if you are told to convert that to degrees Celsius, that will be 283 minus 273. I'm sure we can see it in the slide there. K minus 273. By the time you do that, you have 10. Now, this is what the map looks, the graph looks like. is moving from negative to positive. This from minus 273 up to the positive side. On your x-axis, while on your y-axis, we have the volume. So a practical question is this. At 17 degrees C, a sample of hydrogen gas occupies 125 centimeter cube. What will be the volume at 10 degrees C if pressure remains constant? Remember what we said, V1 T1 over V2 T2. And still recall the temperature must be in what? Kelvin. So we have our V1 as 125 centimeter cube volume. V2 is unknown. T1, remember, here it is given in degrees Celsius. You must convert it to Kelvin. So how do we convert it to Kelvin? We did 17 plus 273. And what did we get? 290 Kelvin. Now, for T2, we have 100, which is its temperature, T2, plus 273. And what do we get? 373 Kelvin. So that's how we converted both temperatures in degrees Celsius to Kelvin, just by adding 273. Please, this is very compulsory, very important. Once you are working with gas laws, all your temperature must be in Kelvin, unless otherwise stipulated that you should convert to Celsius. It must be in Kelvin. Now, putting that into the formula, looking for V2, we have V2 equals to your V1 times your T2 all over your T1. Do we get it? So that's why we have 125 times 373, which is your T2, divided by 290, which is our T1. So if you try that, you will have 161 centimeter cube. Please, I'll give us a few seconds for us to quickly scribble that out so that we can try it on our own, please. So that is for Charles' law. We've talked about Boyle's law. Boyle's law relates pressure and volume. Charles' law relates volume and temperature. So we move. Next, Dalton's law of partial pressure. This law is very simple. This law states that if there is a mixture of gases that are not combined chemically together, if they are not combined chemically together, then the total pressure exerted is a mixture of the partial pressures or the individual pressures that make up the mixture. Say, for example, we have three gases, hydrogen, oxygen, and nitrogen, that form a mixture. The total pressure is adding the pressure of these three gases. That is, you add the pressure of your hydrogen, add the pressure of your nitrogen, and that of your oxygen. It will give you the total pressure in that container, as long as it is not combined chemically. So that's that for Dalton's law of partial pressure. It's just very simple. Add all the pressures together and get it. So that's why we have P total equals to PA plus PB plus PC. So that's for partial pressure. It's just that simple. Now, there is something we call the general gas equation. What the general gas equation does is it combines your Charles law and your Boyle's law together. Why? Notice that for Boyle's law, V is inversely proportional to pressure. That is, V is inversely proportional to 1 over P. While for Charles' law, V, the same V is directly proportional to T. So when we combine all of this together, we have V is inversely proportional to 1 over P and C directly proportional to T. Or if we introduce our constant, we have V equals to T over P, or V equals to KT over P. Remember, K is your what? Constant. So now, if we bring out the constant, leaving your values, that's your PV and your T, what you have is K equals to PV all over T. So mathematically speaking, so I try to make sure here it looks more like what you will write out in your notes. To be P1 V1 over T1 equals to P2 V2 over T2. So even if you do not know exactly how to, let's say you do not remember which is Boyle's law, which is Charles' law, you can store this in your head. Just store P1 V1 over T1 equals P2 V2 over T2. Well, how this can work is, let's say you are given a question and you are not sure which of them you are looking for. By the time you write out your parameters, it will tell you which values are not given and which one is a constant. By the time you know your constant, you will easily solve the question. Say you are given a question whereby temperature is not given. You just know that you are using P1 V1 equals P2 V2. If you are given a question whereby volume is not given, or sorry, whereby pressure is not given, you know that you are just using your V1 T1 over equals to V2 over T2. So this general gas equation combines the two together. While there are some questions where they might ask you, let's say in WAEC, to state Charles' law or Bell's law. For like JAM will only ask you to solve questions based on it, not really to state the laws. That's for general gas equation. So we move to the ideal gas equation. Now, for ideal gas equation, it still works with your general gas equation. But now our constant is represented with R. Notice it there, PV equals to RT. Now the R there stands for the constant, which is the molar gas constant. The molar gas constant is your R. Now, at standard temperature and pressure, the volume of all gases is said to be 22.4 dm cube. At standard temperature and pressure, the volume of all gases is said to be 22.4 dm cube. Please do not forget this. It's very important. There are some questions that they do not give you the volume, but they'll just tell you that as standard volume. So once you see that kind of a question, you know that they're telling you to use 22.4. Now, the equation above, that is PV equals RT, holds for 1 mole of gas. But in the case whereby the number of moles of gas is not given, the formula used is PV equals to nRT, where N there means number of moles. Say you are given 5 moles of gases, 6 moles of gases, 7 moles of gases. You just put that number there in that place for N. So how do we know the value for R now? We know that for pressure is 1 atm. We know that volume is 22.4. We know that standard temperature is 273. And now, standing in for 1 mole of gas, we have R is equal to 1 times 22.4 divided by 1 times 273. That is what we did here. We made R the subject of the formula. We put P to be 1 atm, V to be 22.4, equal to N, which is 1, R not given, divided times T, which is 273. So making N the subject of the formula, we have 1 times 22.4 divided by 1 times 273. If you calculate that, what you have is 0.082. So the molar gas constant is always 0.082. In a question, or if you're given a question whereby you have to use this, you would be given the molar gas constant. So do not really bother yourself, but this is how they got the molar gas constant, using all the values of a standard or an ideal gas. So please recall, the ideal gas equation is PV equals to nRT. So we move now to the next law, which is Gay-Lussac's law. I hope we are following through. I hope I'm not too fast today. I want to just try to cover it. So Gay-Lussac's law. Or is there any question so far, please? Any question? If we have any question, we can just raise our hands, please. No question, right?
No question.
Okay, I'm listening.
Sir.
Yes, you can go on, please.
Okay, the ideal gas law. I can't really understand, sir.
The ideal gas law. Okay. So, so let me just take it again back.
Yes, sir.
Okay. So now, notice this line. PV equals to nRT. Have you seen it there or have you seen it there on your screen?
Yes, sir.
Good. Now, this PV equals to nRT is gotten from our general gas equation. This one here. K equals to PV over T. But now, instead of K, we now use the constant as R. Do you notice now?
Yes.
The constant is now R. Now, remember, we're talking about an ideal gas, a normal gas, a perfect gas. So to represent that, when I say, okay, let us say we have 1 mole or 1 molecule of that gas. That's where N is coming in. 1 molecule of that gas. Now we have 1 molecule of that gas. We need to find out, okay, what is our R? We know what P is. We started what P is from the beginning. That P is either 1 atm or 760 millimeter mercury. But here, to get this, we use 1 atm. As I've said earlier also, volume, standard volume of all gases is 22.4 dm cube. It's scientifically proven. It's not me that found it. It's scientifically proven. Now, for N, since we are focusing on 1 molecule of a gas, N here is represented with what? 1. Then T represented with 273 Kelvin. Remember, we said all temperatures should be in Kelvin. So what we are now trying to do now is, okay, what is our R? If we are given a question, let's say we are given a question that, okay, find the pressure of an ideal gas, or find the pressure of the gas with so-so volume, so-so temperature, and so-so number of moles. How do we solve that kind of a question? You have R. So they use all these values to now get what R is. Imputing everything, what they get is 0.082. So that means anywhere we see R, the value should be 0.082. Like I said earlier, if you are given a question that you need to use this, you'll be told that R equals to 0.082. But it's just good we know how it is gotten. But generally speaking, the ideal gas equation is just that PV equals to nRT. When you impute your formula and you impute your values, you will know exactly what you are looking for. So is it clear now, please?
Yes, sir.
Okay, thank you very much. So, Gay-Lussac's law. Gay-Lussac's law of combining volume states
you
that...
have 6 minutes to go.
Okay. So, Gay-Lussac's law. Gay-Lussac's law of combining volume states that when gases react, they do so in volumes which are in simple ratios to one another and to the volume of the products, if gaseous, provided that the temperature and pressure remains constant. The point here is when gases combine together, they do it in simple ratios. Let's say what they're saying is 1 mole of hydrogen to 2, let us say nitrogen is combining with hydrogen. It will be 1 mole of nitrogen to 3 moles of hydrogen. That is just it. Simple ratios. That's what the Gay-Lussac law is talking. Number of molecules, equal volume of all gases at the same temperature and pressure contain the same number of molecules. So what you're saying is, if we have hydrogen gas with oxygen gas at equal volume, say 11 dm cube, and at the same temperature and pressure, these gases will contain the same number of molecules. And with this, we have what is called the presented as 6.02 times 10 raised to power 23 particles. What does this imply? It implies that if we have 1 mole of carbon dioxide, that 1 mole of carbon dioxide contains 6.02 times 10 raised to power 23 molecules. If we have 1 mole of carbon monoxide, that 1 mole of carbon monoxide still contains, it contains, as long as it's 1 molecule of that gas, it will be 6.02 times 10 raised to power 23 molecules. Now, how does this really make sense? Let's look at this drill below. It says, how many molecules are there in 4.0 moles of ammonia gas? How many molecules are there in 4.0 moles of ammonia gas? Please, can we try it? Can anybody quickly try it for us? That's our drill for today. If we say that 1 mole of each gas contains 6.02 times 10 raised to the power 23. Now, this question is saying there are 4 moles of ammonia gas. If there are 4 moles of ammonia gas, what is the number of molecules? How do we solve it?
Should be 4 multiplied by 6.
We'll multiply that 6.02 times 4.
Beautiful. So please, what's the answer? What is the answer, please? What's the answer? Yes.
It's 2.408 times 10 raised to the power 24.
Okay, that's a good tryout. Thank you very much. And you are right. You are right to an extent. So that's it there. So by the time we just put 1 mole of ammonia contains 6.02 times 10 raised to the power 23, 4 moles will contain how many? So by the time we interchange, we have 2.41. That is what we have. So it's that simple. Whenever you have 1 mole of, just equate 1 mole to 6.02 times 10 raised to the power 23, and then you can now multiply with the number of moles you're expected to look for. So this is where we will end the class for today. I will try and send class drill, but this time around, please, I would want us all to try with the drill, please.
So the ones
help us see how
that
much
was
progress.
done, you've not given us the feedback. How was it?
I've already done the correction at the beginning of the class.
Oh, okay then.
Yes, I did the correction at the beginning of the class. They tried, but then I've already given the correction. I just hope that we've all taken note of it. So this is where we end today, please. If there's any question, we can quickly get to it before the time is up, or we send it in later. Is there any question? Even if it's from the last class, anything we did not quite get, just quickly before the time is up. Hello. Okay, so since there are no questions, please let's not forget when we are dealing with gases, we have to always convert the temperature to Kelvin, which is 273 Kelvins. Either you are adding or subtracting depending on what you're supposed to do. And basically, all these gases, the parameters we deal with is pressure, volume, and temperature. And we've talked about all the laws basically that deal with gases. So just hope we enjoyed the class this evening. Okay. Thank you very much.